We talked about the unit circle and special right triangles inside of a unit circle and knowing the coordinates or the corresponding coordinate points to those special right triangles, 30, 60, 90 triangles and 45, 45, 90 triangles. Now in 1803, Meriwether Lewis and William Clark set off on an expedition leaving St. Louis, Missouri to Astoria, Oregon, well what is now Astoria, Oregon. That's where the Goonies was filmed. And they had with them a guide that helped them navigate the Native American territories that they were going to cross through the western portion of the United States. And her name, of course, was Sokotoa. Just kidding, it was Sacagawea, but I thought that was a funny joke. If you like that joke, make sure to hit the like button and subscribe. But we have these trig ratios, and these trig ratios are just the ratios of the side lengths of a right triangle with respect to an angle. And there are, well, there's really six of them, but the three primary trig functions are sine, cosine, and tangent. Okay, so this is sine, cosine, and tangent. And I joke about Sokotoa before, but Sokotoa is perhaps the most famous mnemonic in all of math that allows us to kind of quickly remember what these trigonometric ratios are. So here we have a triangle kind of drawn in standard position, and the angle we're going to reference, the angle that we're referencing for these trig ratios is theta. Theta is the Greek letter we use when we are assigning basically a variable to an angle. What's the most common one we use? There's other ones we use, but theta is like the main one. So with respect to this angle theta, directly the opposite side of the triangle, right? The opposite side is, we call that side the opposite side. The side that's next to it or adjacent to it, we call that the adjacent side. And then the hypotenuse of a right triangle is the hypotenuse of a right triangle. So what the sine with respect to an angle is talking about is the ratio of the length of the opposite side to the length of the hypotenuse, or O divided by H. Sine is opposite over hypotenuse. Okay, cosine is the ratio between the adjacent side and the hypotenuse. A over H. Cosine is adjacent over hypotenuse. And tangent is the ratio of the opposite side divided by the adjacent side. So O divided by A. Tangent is opposite over adjacent. And these are really important. These trig ratios are fundamentally important to trigonometry. They help us when we get a little bit more involved when we start talking about functions, but they're a way in which we can manipulate, given certain information about a triangle, we can use these ratios of known values to find different information about the triangle. Here's an example. Okay, here's a triangle, and I have two sides of it. The two legs of the triangle are 4 and 5. So the first thing I need to do is find out what this hypotenuse is. So I have the adjacent, I have the opposite, and we know that the hypotenuse, that a squared plus b squared equals c squared. Okay, so if a, let's call it, this was a, and let's call this b. 5 squared is 25 plus 4 squared is 16, and that's going to equal c squared. Okay, so 25 and 16 is 41, right? So CC would be the square root of 41. Okay, so this is square root of 41. Okay, so if I wanted to know on this example, if I wanted to know what is the sine of theta for this example, I would say it is the opposite side divided by the hypotenuse. Right? So sine is opposite over hypotenuse. So the opposite side of this triangle, the opposite side with respect to theta is 4, and the hypotenuse is the square root of 41. If we rationalize this, that's going to be 4 times the square root of 41 divided by 41, because we'd multiply the top and the bottom of this ratio by the square root of 41. Cosine of theta is the adjacent divided by the hypotenuse, so it would be 5 root 41. 5 divided by root 41, sorry. If we rationalize that, it would be 5 root 41 divided by 41. And then the tangent, with respect to that angle theta, would just be the opposite divided by the adjacent. So this one's easier, it'd just be 4/5. We don't have to rationalize that or anything, obviously. Okay. The next step is to talk about how those trig ratios work inside of the unit circle. And this is actually very simple because one thing that we know for all triangles within a unit circle is that the length of the hypotenuse is always 1. It's the radius of the circle. And that this distance, this side length is x and this side length is y. So if this is my angle theta, then I could say the sine of angle theta, the sine with respect to angle theta, is the opposite, right? So I'm going to write SOHCAHTOA up here. SOHCAHTOA. The sine is the opposite, or y, divided by the hypotenuse, y over 1. We could just call that y. Now that's only true for a unit circle because r, right, the radius of the circle was just 1. The cosine of theta is equal to y divided by, the opposite is x, right? Cosine is opposite, cosine is adjacent over hypotenuse, right? So adjacent is x, divided by the hypotenuse is 1, so that would just be x. And then the tangent with respect to angle theta is the opposite divided by the adjacent, so that would be y divided by x. Now, generally, if this was just any circle and we had a triangle within a circle drawn in the standard position like this one is, then we could say like the sine is y divided by r, cosine is x divided by r, tangent would still be y divided by x. We can additionally say here, because if we notice, right, if we notice that tangent is y divided by x, well, we know that sine is y and cosine is x. So we can say that tangent, another way to write tangent, is as a ratio of the sine of that angle theta divided by cosine of angle theta. And so what this does, right, if this coordinate point, we used to call it xy, we could say now that coordinate point, the same, we could just as well say, because it's the same thing, that this is really cosine theta comma sine theta, right, instead of x comma y. And that's kind of a really important connection we need to make between the trig ratios and coordinate points on the unit circle. Okay, so now let's go back to those special right triangles within the unit circle. And we were able to generate these coordinate points by looking at the 30, 60, 90, and the 45, 45, 90 right triangles, normalizing them to have a hypotenuse of 1 because all of these have a hypotenuse of 1. And then we placed them there and we wrote what the x and the y were. So let's relate that now back to the sine and cosine and tangent of these angle theta. So 30-degree angle, this is the 30-degree angle here. The sine of the 30-degree angle, we know that sine of theta is y. So this is for a unit circle, sine of theta is y. So here is the y value, right, of 30 degrees of that coordinate point. So the sine of 30 degrees is 1/2. The cosine of 30 degrees, that's the x value, right? So that would be the square root of 3 over 2. And then the tangent of 30 is y divided by x. So y is 1/2 divided by x, which is root 3 over 2. This would be 1/2 times 2 divided by root 3, which is 1 over root 3, which when you rationalize that is the square root of 3 over 3. So the tangent of 30 degrees is the square root of 3 divided by 3. 45 degrees, this one's even easier. So root 2 over 2, that's the x value, right? So sorry, y value. So sine of 45 degrees is the y value. That's the square root of 2 over 2. Cosine of 45 degrees, that's the x value. I did that backwards, but you see what I did. They're the same anyway. And then if you divide something by itself, you get 1, right? Tangent of root 2 over tangent of 45 degrees is y over x, which y is root 2 over 2, x is root 2 over 2, so root 2 over 2 divided by root 2 over 2 is 1. Moving on now to the 60-degree angle. Okay, the 60-degree angle, which is this one. Okay, that's a 60-degree angle. If we want to know the sine of 60-degree angles of 60 degrees, that's the y value, so it's root 3 over 2. The cosine of 60 degrees, that's the x value, 1/2. And then the tangent of 60 degrees, that's going to be root 3 over 2 divided by 1/2, which is root 3 over 2 times 2 over 1, which is just root 3. So the tangent of 60 degrees is square root of 3. And so these values, right, all of these right here, should be I don't want to say they're easy, because that implies that this whole subject is easy, but they're pretty straightforward. We can pull them straight off of looking at this first quadrant of the unit circle, which itself was not very difficult to generate just based on our understanding of the relationship of side lengths between a 30, 60, 90 and 45, 45, 90 right triangle.